Well, hello everybody. It's a pleasure for me to be here at the Developer Days and presenting you what is basically the work that M31 has been done in the last year. Just a few, yes, as he said, my name is Fabio. I'm the CTO of M31. Just a couple of slides from M31, just a couple of minutes. M31 is a technology startup generator. This is important for what we'll discuss in a few minutes, because the work of M31 is not in the construction and sale of new products, but basically our business model is creating new products, which are frameworks, and then build a new company around that and let the new company bring the product on the market. So we decided to adopt this strategy of new code generation. In the last 2 years, we made 5 new companies with over 70 employees. We are Intel Embedded Alliance members since 2008, and I'm proud to say that we just entered the Nokia Qt partner group a few months ago. So why is Qt critical to M31? Whoever runs a startup knows that running a startup is a totally different business from running a standard company. Startups need to arrive in the market in the shortest time. They have very limited R&D budgets. They must be technologically innovative because they are new companies, so they can't arrive on the market with usual product. They have to be radically innovative. And they have peculiar R&D problems. They often have unstabilized hardware requirements, and they have a low budget, as we said. So choosing the right framework for a startup is critical. So Qt in M31 has been a strategic decision for me, because basically what we're trying to do is to transfer the Nokia advantages to the startups. So Nokia Qt allows for a fastest time to market, and this is what we transfer on the new codes. Qt is cross-platform, is multi-platform, so we transfer this as an advantage to the new products, and it's extremely efficient. So it's a very best framework for our frameworks. So by entering now in the framework that we cover now, it's called SAN. It's a Sensor Actor Network. So what are the current trends in the market today? Well, these things will be probably already covered by many of the talks during these developer days. The current market, as we all know, is going toward the continuous connectivity, toward fluid graphic and intuitive user interfaces. Whatever comes out in the market now, if it doesn't have a fluid, intuitive user interfaces, it's not a big deal. And the market is going toward multi-device, multi-vendor, multi-OS. This is what the future is. We can be happy or not about that, but this is what the future is. On the other end, manufacturers have other problems to face. They need to be on the market in shorter and shorter times. This is a very big problem. They reduce development costs because they have to be competitive, especially after 2009. And they have to be agile and efficient. So you go to a developer and say, I want to be multi-device, multi-vendor, and you have to do it in 1/10 of the time and 1/10 of the cost. This is a problem. So it's a very difficult challenge. In the industrial market, there are even more features. Technology adoption is lower. Market is very segmented. And trying to convince our customers to adopt open methodologies, open standards, is very difficult. And they often cut costs on the hardware. So you find yourself stuck with very power-limited hardware. So they ask you to do whatever web application on an 8-bit processor. So, I mean, this is what you meet every day in the industrial market. We all know about this. So this makes even more difficult challenges. A couple of words about what Juniper in 2009 called the rise of the machine. This is something that will happen in the next years, between now and 2014. That is the number of machines, embedded computers, speaking to each other will rise dramatically. This means Juniper has forecasted that there will be 500 million units of embedded boards that is not consumer boards like smartphones or other things, but embedded boards in industrial applications that will speak to each other, 500 million boards. They will be all on the internet, and they will all consume bandwidth and doing advanced processing. So this is something we have to be extremely careful to. Example, machine-to-machine devices are, for example, healthcare devices. This is just a few examples to give you an outline. Healthcare like patient monitoring, like a Holter monitoring in real time, connected to the hospital computers, or connected buildings. There are companies that are building energy profile monitors to monitor the energy efficiency of buildings. So you have this huge number of sensors scattered around the building, and they are sending all the information to the computer, and mostly over the internet as well. We have smart meters. You know that Google is working on smart metering and so on. And we have, in M31, we have customers asking us to do smart factories, smart productive installations for lean production. They want to have smart roads. They want to have smart everything. So basically, we are moving toward the smart things. And smart does not only mean that is computing in a smart way, but also that is connecting on the internet and talking to our devices. This poses some serious challenges to developers. So by trimming down the problem to the industrial automation, that is what we'll cover today, this is a project that we took last year, that we started last year, and the demand of our customer were very simple. We want to be multi-vendor, multi-manufacturer support. We do not want to be closed on a closed architecture. We want to be open. We want to be open on the web, and we want to be able to talk with other devices with XML and JavaScript and JSON and REST and so on. We want to have true integration with smartphone. We do not want to have a small application doing web queries like a web page, but we want to have very fluid interaction through smartphones. And we want to have a very strong integration between all the sensors of the architecture that we'll see. We want to have devices speak to each other, exchange data, conditionate each other. If I am a thermal sensor that I have a temperature, I have to tell you that you enable the heater and so on. And this needs to be totally automatic. They want to have internet access and a very good user interface. This was the technical specification. So this is what our project leader had to face. He built a sort of clouds of what was needed in order to fulfill the project. And when it turns out that you need all these things in your system, the mess that you see here on the screen is basically the mess that the developer has to face when he tries to outline a project. Because we are not speaking about an innovation of something that was existing, but we're speaking about a new project from the ground up. This was a totally new technology that we had to develop. So this makes you a good drawing of what we normally face when you have to build a new automation system. So our vision at the very end, after considering all the requirements, was to build a system that was dealing with things. Things are sensors or devices or actuators like motors, electric doors, fire alarms, anything that you think. Any device in a building, from monitors to gates. Anything should be able to supply information, like a sensor, or receive information, like an actuator that receives a command, like a door that you say close or open. Or both, because we have devices that can both be source of information and receive commands. And these things should be able to interoperate efficiently, interoperate with other platforms and software. This was a requirement. I want to be able to speak with my management software I have already installed. I want to interface on the web. I want to interface with user efficiently, and users should have a very good interface, and so on. So our approach was to take the most advanced hardware on the market in 2009, take the most advanced software framework, and take the most advanced market and community trends and mix well and deliver this to the industrial market, which translated to obviously getting Qt and MeaGo. This is what we are using ARM9 and Atom processors, and these are the trends that we decided to adopt. Doing smart things, which are based on open protocols, which are always connected, which are very usable thanks to particularly fluid user interfaces, and which are always on the web. This is what the SAN is all about. This is why this talk is about Qt driving this innovation. So let's see why Qt is helping us in this work. It's quite logical. The multi-vendor hardware support is native in Qt, so this was a no decision, basically. We support any kind of appliance thanks to the use of custom drivers that we write and that abstract the description of the devices in XML. Multiple bus support. As you know, in the industrial and home automation, there are a plethora of buses. There is Connex, there is CAN, there are serial buses of every kind. So one of the requirements was to have multiple bus support. And the number of buses to support was not known at the beginning. So we needed to be also future compatible. So we did something that we called virtual bus, which basically is an abstraction of all the buses. The communication protocol was open as well. In fact, we use XML with Qt. The logic and event language to perform all the interaction is done thanks to Qt with QtScript. It's a JavaScript engine. The graphical user interface, obviously, we didn't use Qt. Of course, we used Qt with OpenGL. And we used a touchscreen with gesture recognition. And here we didn't use Qt actually to do the JSON REST interface, but this is something I hope that the Qt team will address soon. And the very important thing is that the customer obviously want to be very short as time to market and very low on cost. So we did all this by maintaining very low both the development costs and the time to market. Okay, this is just another look of what we did. It's quite chaotic, but it's quite simple to understand. Your building is here. There is a house here, which resumes a building. This is an actuator board. It's just a board with that open doors, turns on cameras, and so on. It's a low-tech board. You see lights connected here, alarms, switches, and generic sensors. What we do is that this is a proprietary bus. We receive the bus on our gateway. The gateway abstracts the bus in a virtual bus, which is an XML bus. And this abstracts the devices both on the internet, where you can control the system wherever you are through a smartphone or computer. As you can see, the sensor here is the same here, just to let you understand that you abstract the thing and you find it in your smartphone on the other side of the planet. Then you have local interfaces through dedicated touchscreens or through smartphones locally. So what you do basically when in your building you have this board, which is the core of our technology. When you have this board in your building or installation, you can access to everything, both from outside of the building and inside. You can limit it to what you need, but basically it's very open. So how does it work? Basically, the core of the technology are our SAN gateways. SAN gateways are software and hardware modules that basically act as bridges between the proprietary technologies that you use, like a Connex bus or a CAN bus, whatever you use, and our abstraction layer. So basically, they are gateways. The abstraction layer is what blends all the sensors and actuators and the different buses and the different users. It blends all this in a coherent bus agnostic, usage agnostic, device agnostic model, and this is run by native Qt, XML and JavaScript. This line is very important. When we say we are bus agnostic, usage agnostic, and device agnostic, it means that we need to be so in order to be multi-vendor support, multi-protocol support, multi-OS support, because when you need to be open to everything, you need to be agnostic of the final use, and you have to abstract everything. This is the Sun itself. Then we have Sun clients, which are smartphone application, user interfaces, web services, whatever interact with us and supply the final service to the user. This is probably better outlined. The virtual bus, well, we have all the buses here. We support a huge number of buses. These are just a few of them, just to let you understand what we are talking about. We have, for example, a ZigBee, or generical the whatever wireless 15.4 stack there are in the industry. We support ZigBee, which is normally used in sensor, in smart meters, in actuators. We support the Ethernet as a transport protocol. For example, it's used for custom streaming or for intranets with non-standard protocols. Or if you use Ethernet to go in the internet, then you have websites and web services, smartphones. We support, obviously, Wi-Fi and so on. And I've put here a couple of buses like Connex, which is commonly found in home automation systems, and the LNA, which is not a bus, basically, it's a protocol which is going to be supported in most television and multimedia box. It's used to exchange multimedia contents, basically. So these are the low-level buses. What we do is that we are able to interact with each one of them, and we are able to abstract all these things through a virtual bus. Every device that can connect to one of these buses is then described in XML as an object, as a thing that can provide information or receive command. There are some attributes which are very easy to describe, which tell to our system if a smart meter is able to say what temperature it is, or if a meteorological sensor can tell us what the wind is, and so on. We can receive all this flow of information through the virtual bus. We abstract it in our abstraction model, and then we are able to make all this information interact together and go to other things of the structure. So if you have your sensor that needs to move a Connex actuator, you do this path, you do all the logic here, then you come down and go to the Connect bus. So basically what it happens is that notwithstanding what bus you are using, all the objects are part of a common, coherent structure. So it doesn't matter if you're having a PC with a Wi-Fi interface or a sensor on a ZigBee stack. It doesn't matter. You have all these objects interact together in a transparent way. By going down to the object itself, so we can see some metal here. This is a typical one of the gateways that we manufacture. It's an Intel Atom-based gateway, and it's connected to a touchscreen with a graphical user interface. This is the core of the system. This unit here, as you see, has a serial. Here's a serial bus, has some USB ports, and has a ZigBee interface on it. So this particular model is able to take mostly all of the serial buses, RS485, all of RS232 buses, and ZigBee. We're able to connect. We have different gateways with different devices on board according to what bus you need to interface to. So we have Connex version, CAN version, and so on. Some of our gateways are based on Atom when we need to have when you need to have a very fluid graphic interface. But if you don't need to make any graphic interaction, we can use ARM9 processors like the IMX28 or IMX27 from Freescale, which are very low-cost devices. So it's very flexible. We just recompile the Qt stack here. It's just a couple of hours of compilation, and it works. So just to show you what we are talking about, this is sorry for the very bad video. We did it before leaving here. This is a user interface which shows you a user interacting with one of these installations. This is a house with with a couple of floors. when you enter into the house, you can interact with all of the objects. The objects are on industrial buses or on Connex buses or on ZigBee. As you can see, the operator is interfacing with the system through a very fluid interface and very easily. He just clicks on the device and actuates it. There is no need to do very complex manipulation of the objects. It's very intuitive. You go to the object and you click it. That's all. It's the underlying structure that drives all the interaction between the different buses, the different protocols, and resolves also all the different conflicts between the protocols. Here, for example, you can see a graphic which is supplied by which is supplied by a smart meter, which shows you the power consumption of the devices. So this was just a brief video to show you how the user interface is. Because being an automation system, we have not a lot to showcase here, but we can just showcase you the interface and the boards which are down in our booth. This is what the interface is. By going down to the features, let me just show you a couple of features that this system performs, which are very critical. First of all, the virtual bus is a very, as you have understood, it's a very important feature because it allows the system to speak to any device. And it is future-proof. It's an open protocol. So whenever somebody pulls out a new protocol, a new industrial stack, it's just a matter of writing the XML interface for it. It's just a few weeks of work, if we know the protocol, obviously. Virtual bus, what does? Virtual bus is just a way to interface systems on bus A, which are here in blue, systems on bus B, generic bus B, and systems on bus C, which are here in orange. We can have different gateways, because each gateway can interface to one or more buses. And the gateways have the ability to blend to each other. So once they connect to the proprietary bus, they form a sort of cloud. And they are all interfacing to each other in a very transparent way. So when you have the operator interface, which can be connected to bus B, but to this gateway, but it can also connect to this gateway or this gateway, it's the same thing. The operator sees all the objects as if they were on a single bus. And the installer of the system also programs the devices and the interactions as if they were on a single bus. This is a very important feature. A second feature of our system is that the abstraction can happen not only between different buses on the same building, but it can happen also between the gateways on different buildings. So you can have a sort of virtual building which connects devices on geographically different locations. So you can go to your industrial installation manager and say you can have one interface to control all of your production sites. And you can manage all them in the same interface. And you can have the installations interface and interact with each other if you need to. And a very similar approach is when you have a very big building, you are very scalable. So you can sort of abstract all of the different gateways in the different sides of a big hospital, each one with its functions, and you can abstract it through the web to a very simple interface. So whenever you have some installations where it is required to have a centralized control, a very simple control on a single interface, you can do it with this system. So the advantages of using Sun, which are the advantages we had in using Qt for doing this technology, is that the vendor manufacturer has a very low time to market because this technology is already here. He just needs to customize for its own use. Low production costs and low R&D costs because the developer, the R&D unit of a manufacturer just has to translate its protocol in XML, and this is a very easy task. The vendor is also future-proof because the system is already enabled to be adaptable to whatever comes out in the future. It's very scalable. It's very flexible. it is able to retrofit existing systems, which is very important in industrial installations because most of the manufacturers already have big installations on the field. They cannot change the technology. So you have to be able to retrofit. So you just, if you use a very old technology, you just describe the protocol in XML, use an appropriate gateway, and you're ready to go. You have hassle-free integration because the programming interface is very simple. You just use JavaScript and XML. You do not have to work with the very strange or very proprietary interfaces and so on. So it's very easy to integrate systems through SAN. And you have, being an open system, the vendor, if he wants to, he can open his system to communities over the world. So maybe you want to do a home automation system, and you want to open it to the communities. So the people can write their own widgets to control the dishwasher, the refrigerator, if it's the case. So he has great value here. The user, finally, I mean, each one of us would like to have a good home automation system, but I mean, there are not very good home automation systems right now. I've just bought my new Samsung television, and I would like to see the widgets there coming from my computers. I can't have it. I would like to have my brand new refrigerator having a widget on my television. You can't do this. So by adopting this kind of technology, you can have true system integration. You can have ubiquitous monitoring and control of everything, basically, because through your smartphone, you can go around and connect to your SAN installation and control every device. You can simplify very complex systems whenever you have very different buses, which needs to be interfaced one to each other. You can do it through this. You have a single remote control for all of your systems. You do not have 3 or 4 devices, one to connect to a particular bus, the other to connect to another bus, and so on. You just have a smartphone. You integrate your own platforms, and again, you have great value. Just a couple of slides to show you other examples of this same technology, because what we spoke here was to as a deployment to a home automation system. Here we have another couple of examples of similar projects that we did adopting this technology. One was this Albert system, which is a system to do cooperative distributed video surveillance. This was a customer, a big customer that manufactures next generation of video surveillance devices. They are autonomous video surveillance devices that are able to do very advanced video content analysis. They have a very sophisticated event engine that is able to perform a lot of very peculiar tasks on video surveillance. And they needed these devices to be all connected to each other and all speaking to each other. So we adopted the same technology. So these are the features that we developed there, but it was just to give an example. This allows them, the fact that the system is integrated and coordinated means that they do not have the control room anymore. I mean, whenever you go to a video surveillance system, you know that there is a control room there. If somebody disables the control room, you have disabled the whole system. While here, since the objects speak to each other, for example, if there is somebody that does something bad into your building, he has to destroy all of the devices to destroy the memory of what he did. Suppose that somebody does something and there is the image of what he did. He has to go and destroy every single sensor because this image has been sent to everybody. It's like a RAID system. So it's quite innovative. This gave 4 patents on this project. Another very interesting project is this interface, which seems to be very simple, but it's another installation of our system. We had a manufacturer, the biggest manufacturer of plastic corks, the corks that are used on liquor bottles, that came to us and said, I want to be able to, I have many factories around the world, and I would like to be able to have them on my smartphone. I want to be able to see in my smartphone the running machineries that are producing the corks, and I want to be able to have a delivery time of the number of corks I'm doing, because I want to be able to know what my factories are actually producing. maybe a customer of mine calls me and say, when are you delivering me this bunch of corks? And I want to be able to give him a reply immediately without having to call the production manager and so on. So what we did is that we used the same technology. We took their machineries with one of our servers, and the machineries through Sun are connected to our servers, and he can control directly with his smartphone the machineries in his industrial installations. This was called in ESCAP. Anyway, it's again Qt with the SAN. It's the core gateways have a preliminary MIGO interface in them. They connect to an industrial home bus device. They perform data fusion because there are a lot of data to be extracted to extract that information and so on. So if you are if you want to take a look to, I'm sorry I don't have anything other than the movie to showcase here, but if you want to try with your hands one of the graphical user interfaces, you can come down to our stand, to our booth there, and you can try our industrial automation interface. So you can play with it and see how it works. What we brought here in DevDays are, as I recall it, it's a ZigBee. It's a mashup between ZigBee, Ethernet, and the serial product industrial interface. So you can interface all the objects, and you see the smooth interaction between the objects residing on different buses. So basically, the most important thing about this whole presentation is that the whole thing has been done thanks to Qt. If it wasn't for Qt, this would have required a huge amount of work. The 90% of the feature that we were able to transport on the market were transported just taking them from the Qt features. So the multi-platform, multi-hardware, and so on. They were just plug and play with our architecture. So the point here is when you enter the industrial market, you have to cope with already existing technologies and complex architectures. Qt can be of great help to simplify things and to supply some real value to your end user and customers. So this was just an example of what we did. That's all. If you have any questions.